My name is Enzo. I'm a co-chair of PAGES and the president of the Joschke Center for Climate Change Research at the University of Bern, and I'm chairing this second session on regional climate reconstructions, filling the gaps. Focus 2 is dealing with regional climate, regional reconstruction, and the reconstruction of regional climate modes. There are 4 speakers today. The first talk will be on Enzo by Axel Timmermann. The second on Australasian climate variability by Kevin Andriukaitis. And then Matthias Wüy will cover South America. And finally, Jörg Luterbacher will talk about the European climate dynamics. So we start with Enzo and with a talk by Axel Timmermann.
Good morning, everyone, or as we say in Hawaii, aloha. This is a great pleasure and honor to be here, and I would like to thank the organizers and in particular Heinz Wanner for inviting me. Okay, the title of my talk is El Nino, a sturdy companion through time. And this is a little bit a strange title, I have to admit. But anyways, I hope to convince you that it's actually quite amazing how stable Enzo actually is, that we can change tectonic features, that we can change orbital forcing, and El Nino will still be there. So this is something that I find very puzzling and try to understand. And in addition to this stability, of course, there are changes in the behavior of Enzo on long time scales and short time scales. And that's also something puzzling because we don't really understand what are the causes of these smaller term changes of Enzo. So this is work done in collaboration with Shane McGregor. This pointer doesn't work. Stefan Lorenz from the Max Planck Institute in Hamburg, and Yuko Okumura from NCAR. So El Nino, of course, is, or the El Nino Southern Oscillation phenomenon is very well known for its far-reaching global impacts. El Nino conditions and also La Nina conditions impact hydroclimate in many regions of the world. They can cause disease outbreaks. They can be responsible for extreme weather conditions in many regions of the world, and also for coral bleaching and many other impacts on global ecosystems. But there are also impacts that are not as well understood as those, in particular impacts on our everyday life. So this is a typical story from Hawaii. So what is El Nino? What's the El Nino Southern Oscillation phenomenon? The warm phase of El Nino of Enzo is called El Nino. The cold phase is called La Nina. And El Nino conditions are typically characterized by warming in the eastern equatorial Pacific and sea level pressure pattern, the so-called Southern Oscillation, which is characterized here by high pressure in this region and low pressure in this region, and a shift of the convection centers from the western tropical Pacific to the central or eastern equatorial Pacific. So during an El Nino event, a lot of interesting things actually happen. Not only do you have these Rossby waves in the atmosphere emanating from the tropical Pacific that cause the main tailor connections, but also in the ocean important things happen. And here we see the situation in January 97, just almost a year before the major El Nino event 97-98, and we see that prior to the El Nino event we have a charged warm pool. The western tropical Pacific carries a lot of heat, the thermocline is pretty deep. Then in April and July, a series of westerly wind bursts, so episodic weakenings of the trade winds caused Kelvin waves to propagate from the western equatorial Pacific to the eastern equatorial Pacific. That led to a decrease of the thermocline depth in the west and an increase of the thermocline depth in the east. And furthermore, the curl associated with the wind stress anomalies triggered Rossby waves, or the transport that started to discharge actually equatorial heat away from the equatorial region into the off-equatorial regions. And that's a process that takes much longer. And after some time, here around March 98, this discharging that was induced by the wind stress curls has already led to a very strong shoaling of the thermocline that eventually leads to a turnaround of the El Nino event, the 97-98 El Nino event. And that's kind of typical, and you already see that ocean dynamics plays a key role, but also atmospheric features such as these westerly wind bursts, which I will discuss later on in a little bit more detail, can be key features of El Nino events. So El Nino is not just a warming in the eastern equatorial Pacific. El Nino is the warm phase of a coupled atmosphere-ocean mode, and this mode is not only just one mode, it's not one animal, but it turns out that El Nino has many different flavors. And for example, there is a westward propagating SST mode that's depicted here from a theoretical modeling study. This is a Hofmüller diagram. Time goes up. This is longitude, and this is sea surface temperature anomalies. And we are seeing these sea surface temperature anomalies propagate westward here. And this so-called westward propagating SST mode does not involve thermocline dynamics in the ocean very much. There is the interannual mode, which I think most of us are very familiar with. There is a quasi-biennial Enzo mode, which has interesting features, a little bit of westward and eastward propagation together. And there is a warm pool El Nino mode. Some people call it Modoki, El Nino Modoki. And that's pretty much a movement of the warm pool front that occurs on interannual timescales. So Enzo is not just one animal, it has lots of different characters or flavors. So we talk about El Nino flavors. That's something to keep in mind. And it turns out that the background state can actually, depending on the background state, you can either be in a regime where the westward propagating SST mode is preferred, or in a regime where, for example, the interannual mode is preferred, or the other way around. So that's actually quite interesting, and we need to understand how the background conditions, maybe paleo background conditions, actually affect the regime behavior of these Enzo modes. Just to illustrate here, this is the 82-83 El Nino event. It fits actually quite nicely with these theoretical considerations. This is an earlier westward propagating event from the 1970s, I believe. So these theoretical modes actually occur also in reality. So it's getting more complicated because El Nino, the interannual feature that we are interested in, is connected with other features in the equatorial Pacific, in particular the seasonal cycle. And the seasonal cycle is affecting El Nino through its growth in a particular season and growth saturation in a particular season, but also El Nino is affecting the strength of the seasonal cycle. Moreover, the Madden-Julian oscillation, an atmospheric feature, eastward propagating mode in the atmosphere, plays a big role in actually driving El Nino variability. Moreover, there is clear evidence that El Nino itself, or Enzo variability itself, feeds back onto the activity of these MJO events. And westerly wind bursts, as I just mentioned earlier, they can play a role actually in triggering individual El Nino events. And it turns out, via ocean Kelvin waves, it turns out that an El Nino event increases the likelihood of these westerly wind bursts to occur. So here we have an interesting timescale interaction, which we call noise-induced instability. So all of this is pretty much an orchestra of tropical Pacific climate modes or atmospheric modes that all interact in a interesting manner with the El Nino Southern Oscillation. So that's something to appreciate. El Nino is more than just Nino 3 sea surface temperature anomalies. Okay, what controls the amplitude of Enzo? That's a very important question because we want to understand actually how paleo conditions, how external forcings actually impact the characteristics of Enzo and perhaps also its predictability. Well, clearly the background state plays a key role. If we have a very deep thermocline in the eastern equatorial Pacific, it's rather unlikely that we generate very large El Nino events. Moreover, the strength of the annual cycle turns out to be a key player in driving or in determining the variance of Enzo. And coupled model simulations have indicated that if you increase the strength of the annual cycle in the eastern equatorial Pacific, typically Enzo variance decreases. It's not 100% clear, but there is good modeling evidence, which I will show in a minute, that there is actually a competition here. Either the annual cycle is strong and ENSO is weak, or the other way around. It turns out that also the noise level, or manifesting the strength of westerly wind bursts and the Mad-Julian oscillation, plays a key role in driving ENSO and also determining ENSO variance. And there are nonlinearities in the system that eventually cap the amplitude of ENSO. So it's complicated. Let us go back in time and just discuss a few interesting modeling results here. Turns out that if we change the continental features, topography, and so on, in pretty rude and brutal ways, such as going to the Cretaceous, it turns out that ENSO can still survive. So this is from a model simulation that Matt Huber conducted with the CCSM model under Cretaceous conditions. So the Atlantic is barely there. We have high CO2 concentrations. The entire bathymetry of the ocean looks completely different than today. This is the standard deviation of sea surface temperature anomalies. And it looks pretty much like ENSO is alive, which I find quite surprising. I don't know why, but apparently these changes in the boundary conditions, gluing Antarctica, Australia down to Antarctica, doesn't seem to affect ENSO. That's a very, very surprising result, suggesting that ENSO is maybe very, very stable, at least in this model. Now, another time slice, which is quite interesting, is the Paleocene-Eocene thermal maximum. Also, the bathymetric conditions were significantly different. We had an open Tethys passage, Panama was wide open, and this is from a model simulation that was conducted at the Max Planck Institute by Malte Heinemann. What we are seeing here is just the mean sea surface temperature 55 million years ago during the time of the Paleocene-Eocene thermal maximum, and it looks like there is, at least relatively speaking, still a cold tongue here. Well, it's nice bathing conditions here, or swimming conditions. Wouldn't call it a cold tongue, but relatively speaking, it's certainly a cold tongue. And this cold tongue, the existence of this cold tongue, is enough actually to generate ENSO variability. And it turns out that the variance here of sea surface temperature anomalies in that region is in the order of 2 to 3 degrees, which is about twice the amplitude of present-day ENSO variability. So even if we have Panama Isthmus wide open, the thermohaline circulation kind of different, a Tethys passage open, and also Australia much farther down, ENSO seems to be alive and strong and healthy. So why is that? Do we really understand under what circumstances ENSO can change significantly or maybe even disappear? Well, I will go through some other examples that might be quite instructive. The orbital effects on ENSO. And of course, we have several forcing candidates here. The precessional cycle is very important because it changes the strength of the seasonal cycle at any given latitude in the tropical Pacific. And obliquity plays also an interesting role, eccentricity as the main modulator of the strength of the precessional cycle too. So we will focus here on a climate model simulation that was conducted with the ECHO-G climate model, so pretty much a state-of-the-art climate, IPCC-type climate model. And this is a simulation that covers the last 140,000 years. And a little trick was applied here in order to run it for 140,000 years. It's called orbital acceleration. So what I'm showing here is the amplitude of the annual cycle in black, and you see a beautiful precessional cycle here, and the strength of the meridional SST gradient in the eastern equatorial Pacific. Northern temperature in the eastern equatorial Pacific minus southern temperature in that region. And it turns out that the strength of this meridional asymmetry is the driver for changes in the annual cycle strength in the eastern equatorial Pacific. First of all, it's surprising that there is an annual cycle in the eastern equatorial Pacific because the sun crosses equator twice. So the reason why we have an annual cycle in the eastern equatorial Pacific is because the ITZZ typically stays north of the equator. So, however, the precessional cycle, as we heard already from Larry's talk this morning, can have a huge influence on the position of the intertropical convergence zone. And that's basically what we're seeing here. This is a situation when the intertropical convergence zone is rather close to the equator. So we have conditions that are more like the western equatorial Pacific, where we have a semi-annual cycle. And in this case, the annual cycle amplitude in that region in SST disappears pretty much. So the annual cycle is modulated by the anomalous annual cycle forcing from the precessional cycle. So many cycles. Going a little bit more into the details, what's happening here, I'm showing a Hofmüller diagram in the eastern equatorial Pacific of precipitation changes. So this is time from 140,000 years to 110,000 years in this particular run. And we are seeing this is a northern position of the intertropical convergence zone. And then pretty much suddenly, for certain orbital configurations, the intertropical convergence zone can shift southward, actually south of the equator in some cases. And it turns out that the situation where the intertropical convergence zone is far north of the equator is characterized or accompanied by very strong annual cycles. So this is a wavelet diagram of sea surface temperature in the eastern equatorial Pacific. So strong annual cycle, 1 year here, whereas Enzo is kind of lingering around. Then when the intertropical convergence zone hops to the southern hemisphere, the annual cycle disappears, as we saw early on, and Enzo becomes very strong. So apparently the two don't like each other. Well, we'll come back to that later. And what's quite fascinating in this model simulation is that there is abrupt climate change in the tropics. The intertropical convergence zone can jump abruptly. Whether this is something that other models can reproduce is still an open question. Now, how about millennial timescales? And in particular, the question whether changes in the overturning circulation in the Atlantic can have an influence on Enzo variability. In order to study this, we used a series of climate model simulations, and already Larry had this little cartoon here of the water hosing man, the fireman, dumping fresh water into the North Atlantic, and that's basically to mimic a Heinrich event and shut down the overturning circulation. So this is the typical SST pattern that you generate, and wind stress pattern that you generate in any of these climate models, state-of-the-art climate models, northern hemispheric cooling, southern hemispheric warming, pretty much the bipolar seesaw response, and also the trade winds intensify here, leading actually to more surface cooling by enhanced evaporation. Then the trade winds, the anomalous trade winds, see the Coriolis force changing signs, so they go the other way, and they oppose the mean trade winds, and hence you have less evaporation, less upwelling, less mixing, leading also to this stronger warming here. The interesting thing that was noted by Tom Delworth for the first time was that actually this pattern translates also into the Pacific. We have cooling in the North Pacific and warming in the South Pacific. And we have further tried to elaborate on the mechanisms, explore the mechanisms, mechanisms of this Atlantic-Pacific connection in the tropical region. And it turns out that you need air-sea interactions in that region, in particular, in the northeastern equatorial Pacific, in particular, to eventually set up this entire structure for the Pacific Ocean. So, is there any evidence in paleo data that supports this scenario that a shutdown of the overturning circulation leads to a weakening of the mean sea surface temperature gradient in the eastern equatorial Pacific? Right now, we have a warm pool here. Under weakened overturning circulation conditions, we would have no warm pool in that region. So, what I conducted here is an EUF analysis of alkenone SST reconstructions from this region. So there are quite a few cores that have high enough resolution to study actually orbital scale and millennial scale behavior, at least for the last 25,000 years. And the dominant mode of variability, which is, I didn't show the pattern, it's a homogeneous pattern, is pretty much the deglaciation here. But the second mode is quite interesting. The pattern of the second mode is indicated here by the stars. So we have pretty much warming south of the equator, cooling north of the equator. I think one star is missing. And it turns out this is happening exactly at Heinrich event 1. So this is kind of consistent with the modeling results that for Heinrich event 1, or for these millennial scale features that are associated with weakenings of the overturning circulation, you generate cooling in that region, and there is a tendency for warming here. This is just indicative. It's supporting a little bit this model result, or the other way around. Now, what happens if we collapse the meridional SST gradient in the eastern equatorial Pacific? Since the annual cycle in the eastern equatorial Pacific lives on the meridional SST gradient in that region, ITCZ has to be north of the equator to generate an annual cycle. If we collapse this situation, we would expect the annual cycle also to disappear. In 4 out of the 5 climate models we analyzed, this is in fact happening. The annual cycle weakens tremendously. This is a spectrum. Whereas in all of the cases, in all of the 5 model simulations we analyzed, Enzo variance, here depicted in this spectrum, intensifies tremendously. So a weakening of the overturning circulation in different models consistently leads to a strong intensification of Enzo and a collapse of the annual cycle in that region. So is there any evidence from the last 100 years that, at least in terms of tendency, similar things might happen? And now this is very speculative because we don't have enough data, and that's where the paleo data might come in very handy to further confirm or falsify such hypothesis. So what's shown here is the detrended AMO index, Atlantic Multi-Decadal Oscillation, for the last 100 years. This is the strength of the annual cycle in the eastern equatorial Pacific, normalized and detrended also. And it turns out that this period here, warm period, goes along with a strong annual cycle in the eastern equatorial Pacific, and also the cold periods with weaker situation. So that's consistent with the water hosing result, although the water hosing result is of course much stronger in terms of amplitude. The annual cycle and Enzo behavior that was already noted earlier by Gu and Philander looks like there is an out-of-phase or anti-correlation between the amplitude of annual cycle and Enzo. So that's kind of suggestive that this scenario that we try to describe for a water hosing and a complete shutdown of the overturning circulation works even for small variations of the sea surface temperature in the Atlantic, and maybe even for multi-decadal variations of the overturning circulation in the Atlantic. But that's very, very hypothetical here. Now, just focusing on the last 350 years, something interesting, I think, emerges, in particular if we look at different climate proxy data. There are about 9 proxy data available, Enzo proxy data, so publications or time series that claim to represent Enzo variability throughout at least the last 350 years, some of them even longer. And modelers are typically very democratic, so what they do is they treat all these proxies in an equal way, and what comes out is, if you plot all of these proxies, and each of them claims to be a proxy for Enzo variability, it's pretty much a mess. And it turns out that if you look at the inter-proxy uncertainty, so for every year you compute the standard deviation, it's pretty much the standard deviation. The scatter among the proxies is as big as the scatter for El Nino in that entire time series. So that's a little bit of frustrating result. However, the question is, can we squeeze out their joint variability? Is there any joint variability left? And in order to do that, you can conduct an EUF analysis, because that's designed to squeeze out the joint variability, and it will discard proxies that don't fit into the system and are more representative of noise or other features. So we call this, well, it's a little bit a pompous name, but a unified Enzo proxy. And it turns out that, in particular, in the last 100 years, this unified Enzo proxy, the dominant mode of this principal component analysis or EUF analysis, the dominant mode correlates better with the instrumental data than any of the 9 input proxies, so that's already a good thing. Furthermore, we have an interesting feature here. It looks like the variance, if we believe this proxy, the variance of Enzo has increased over the last 350 years, which is surprising. But of course, the first suspicion is that since there are dating uncertainties in these proxies here, maybe we can just, it's a kind of negative interference between these, and you would just get rid of the signal, because basically what an EUF analysis does is it averages in a kind of way. So in order to test this, we did something else. We computed the running variances of all of these 9 proxies. So the dating uncertainty is not such a big issue, and ran an EUF analysis of this. And what comes out is exactly the same trend behavior. So there is some evidence that this trend behavior might actually be a robust feature. And in particular, if we compare this Enzo reduction in the 1650s in particular with Enzo chronologies, so historical data collections, we see that in all of the existing Enzo chronologies in the 1650s, Enzo variance was very much reduced. And the question is, of course, why? We have absolutely no idea why that was the case, but I think it's a rather robust result. And it turns out that a little bit earlier, the Enzo variance was actually higher. But 1650 is a particular period where Enzo variance was strongly reduced. Let me just say 2 or 3 words on Enzo response to greenhouse warming, because it's a conference that's trying to bridge the past and the future. So I think it's interesting to see whether any of these lessons can help us to further constrain Enzo's response to greenhouse warming. Well, first of all, we need to figure out what's the mean response to greenhouse warming in the Eastern Equatorial Pacific. The famous enhanced equatorial warming pattern is shown here. This is the typical response pattern for year 2080 to 2100 in IPCC CO2 doubling scenarios. So it looks like we have strong warming on the equator and somewhat reduced warming outside the equator. Now, sometimes it's quite instructive to compare these response patterns with the mean bias patterns of these models. So here we have a bias of about 4 degrees, we have a warming of about 1.4 degrees. So that's something always to keep in mind when looking at these models. Furthermore, if we look at the mean representation of Enzo in these models, this is the observed standard deviation, there is nothing going on here in the Western Pacific. These are the best climate models in terms of Enzo representation, and it turns out they have this huge variability in the Western Tropical Pacific. So it's rather unlikely that they really capture the right regime of Enzo variability in which we are in right now. A lot of these models actually have an El Nino Modoki regime rather than, let's say, a Koltang Enzo regime. So that's also something that needs to be improved, and that's actually being improved right as we speak right now in climate modeling centers around the world. In terms of Enzo response to climate change, we already discussed that there is a tendency for an enhanced warming in the Eastern Equatorial Pacific, slightly more than in the West, but basically these patterns suggest that East and West warm almost as much, but keeping in mind this caveat of this model bias. And so the variance generated in these models in response to greenhouse warming, in some cases, Enzo variance decreases and increases. So we don't really know what's happening in terms of the Enzo variance. And I would like to finish here with my conclusions, and the conclusions are the following. La Nina and El Nino weather patterns today and in the future. Okay, thanks for your attention.
Thank you very much, Axel, for this exciting overview on past and future Enzo. Please use the microphone if you want to ask a question. We have time for 1 or 2 or even 3 questions.
What you show the technical modeling, does it deny the idea about permanent plyos in El Nino?
Well, not the figures I demonstrated, but I think I actually had a few other figures on the Pliocene background state pattern. I think it can be denied, at least on modeling grounds. And it turns out if you do a careful analysis of the proxy data and take into account the northern and southern SST proxies in the Eastern Equatorial Pacific, the pattern you reconstruct is actually orthogonal to an El Nino event. It's exactly the northern hemispheric, so if you go from early Pliocene to, let's say, late Pliocene, you go from cold conditions in the northeastern Equatorial Pacific to warm conditions. In the South Pacific, southeastern Equatorial Pacific, is somewhat different. So the pattern of climate change from early Pliocene to late Pliocene is the same pattern as that of water hosing. And it turns out that if you go from open Panama Isthmus to closed Panama Isthmus, the overturning circulation is intensifying, and similar arguments as those that I made here can be adopted for this particular thing. And it's consistent with paleoproxy data if you do not only take a core in the north, in the east and west, but you need to take into account the full structure, meridional structure too.
Other questions? Please.
I'm sorry, can you explain why...
Just use the microphone.
Could you explain why it is that the seasonal cycle and ENSO variability should be inverse to one another?
It's a great question. I think no one knows at this stage, and it's not happening in all of the cases, but in a lot of climate model simulations that I looked at in terms of their response to external forcing, they seem to have this behavior. And the key, I think, is the growing season of Enzo, which is typically around spring to summer. If you change things in that season in a particular way, the growth of El Nino can be inhibited. So if you shift your annual cycle or weaken the amplitude of annual cycle in that particular season, the changes in the summer or spring season would inhibit or expand the growth or accelerate the growth of Enzo. So I think if you can seasonally stratify this problem as a growth problem of Enzo variability. But it's not 100% understood, to be honest. And there are ideas that this is the nonlinear frequency entrainment scenario which people in chaos theory use to explain why your pacemaker in the heart is sometimes creating some weird behavior with your heart and so on. So there are mathematical concepts, but it's not a simple intuitive understanding. I'm sorry about that. Yet.